Hello viewers, welcome back. In the last class we learned about the general reaction mechanism, that is for SN1 reaction. Today's class we discuss about the factors affecting the rate of SN1 reaction. Here also, as we discussed for SN2 reaction, the same factors have been involved in the SN1 reaction also. There are four factors: effect of alkyl group, leaving group, nucleophile, and the effect of or nature of solvent. Now let's see how the nature of alkyl group, if we vary the nature of alkyl group, how the rate of SN1 reaction will get vary. Let us take this general reaction. So what will happen? Any alkyl halide, it will form a carbocation plus this leaving group halogen. Later this one react with nucleophile. So we will get, suppose if it is a water, and we will get ROH like this. Now let us consider if that R is methyl or primary or secondary or tertiary. We know that the rate of reaction is depends on the formation and a stability of carbocation. Okay, so this is the key step. First step is the formation of carbocation. If this carbocation doesn't form, then nucleophile will not attack this and we don't get the nucleophilic substitution product. Okay. So that means this is the primary step. So this carbocation is formed and its stability depends on the nature of alkyl group. Okay, if you take the methyl halide and it should form methyl carbocation like this, but this will not at all form in this reaction. The carbocation, the methyl carbocation will not form. The reason is this is not at all stable, or highly unstable. That's why this will not form methyl carbocation. Then why the tertiary carbocation is getting formed? Because this is highly stable due to hyperconjugation. Hyperconjugation is this key step or the reason for the stability of carbocation. Now let us understand what is hyperconjugation. So let us take this example of, this is the tertiary butyl carbocation. This is the molecular orbital diagram. Okay, so this is a molecular orbital diagram explanation. So this is an empty p orbital. This is an empty p orbital. So this one, okay, this one empty p orbital. This empty p orbital overlap with this adjacent the sigma bond. You see, whatever this the green dotted, so these are the dotted one are representing the overlapping of this empty p orbital of this carbon empty p orbital with the parallel this sigma bond, the orbital of this adjacent carbon. So this is called as hyperconjugation. As a result, it has been stabilized. You see here, we are showing only one hydrogen in each methyl carbon. There are total 9 hydrogens in the 3 methyls, means here each methyl containing 3 hydrogens, total 9 hydrogens. That means 9 times it can overlap. If the maximum overlap means maximum stability. That's why the tertiary carbocation is highly stable due to hyperconjugation. Why not the methyl carbocation is not stable? The reason is here the methyl carbocation does not connected with any other carbon atom. So why it does not have any overlap with the adjacent sigma bond. So here there is no adjacent sigma bond for overlapping. Okay. So that is the reason the methyl carbocation is not stable. Now according to the stability order, so the tertiary carbocation forms faster than secondary, then primary, then methyl. So why the tertiary alkyl halide will go, fastest SN1 reaction. The methyl no SN1 reaction. Even the primary also. The secondary is there are chances it can undergo according to the condition. Okay, it can undergo. Secondary alkyl halide has the possibility to undergo SN1 reaction. Even it can undergo SN2 also according to the nature of condition, nucleophile and the solvent. So finally, so this is the order for SN1 reaction. Tertiary will go faster, then secondary, then primary and methyl. Now we are going to discuss one more important concept, the rearrangement of carbocation. So what will happen? Let us take this example. So now this is one alkyl halide. So now this is a secondary alkyl halide. So first step is it undergoes like this heterolytic cleavage and forms a carbocation. So like this. Like this. Here this is the secondary carbocation. Here it can undergo rearrangement to get most stable carbocation. So this one is shifting as a hydride shift. So it shifting to this positive charge carbon. So what will happen after shifting? So this carbon will get positive charge and this will become, this hydride is getting shifted. Finally you will get like this. Now this is tertiary carbocation. Now as we discussed, the tertiary carbocation is most stable than the secondary carbocation. That's why it get rearranged. Okay. So this is the rearrangement because for the stability purpose. Now the nucleophile will attack and finally you will get this product like this. So we are getting the rearranged product, not like here not like here. You see, suppose if the nucleophile attacks here, then we should get this one. But this product is not formed because this carbocation, secondary carbocation, get rearranged to the tertiary carbocation. That is the reason in the SN1 reaction we always get a rearrangement product. So this is one of the drawback in the SN1 reaction because of the rearrangement of carbocation. Hope you will understand the effect of this alkyl group in the SN1 reaction. The remaining factors we will discuss in the next lecture. Thank you.